which is in fact very simple. What is in fact the brain, right? Now in a reductionist view, you can look at the brain as an ensemble of a large number of single cell functional units called the neurons. And there are in the brain about 100 billion neurons. Neurons are connected to each other. In fact, some neurons are connected to about 10,000 other neurons. And a neuron consists essentially of a cell body called the soma. Then there are many protrusions, many elongated protrusions. So a group of them frequently branch out the dendrite. There is a very long and thin one called the axon. Now, as I said, the brain is the neuron is the main functional unit, and neuron process information through an exchange of chemical and electrical signals. And in this actually complex event, there are two main functional units at work. The axon, which is responsible, in fact, to process and generate output signals, and the spines located along the dendrite that, in fact, receive and process input signal. Now, the spines are these tiny protrusions. They are micrometer in size, and they, in fact, are dynamic. They change in shape and size, depending on external stimuli. And the way axon and spines communicate, in fact, by converting chemical signals to electrical signals through the release of some chemical mediator called neurotransmitters. This happens in a complex system here that is what is called the synapse. Now, understanding the complexity of the brain, going from the cell level up to the system level, is a great challenge. It is, in fact, has given recently been formulated into the so-called Brain Initiative launched by the White House in 2013. This is called like the challenge of the new millennium, and BRAIN stands for Brain Research Through Advancing Innovative Neurotechnologies. And if you read the document, which is very interesting and very detailed, some observations are made along this line. It is noticed that, in fact, there have been spectacular advances in molecular and imaging technologies during the last decade. And they are, in fact, open up incredible opportunities for discovery. You hear all the time about new type of microscopes or new type of fluorescent dyes allowing things that were not possible until long ago. It is also observed that these technological advances, in many cases, are not being matched by comparable development in terms of analytical tools, algorithmic tools, computational tools. And here we are not talking just about the usual big data issue of being big. This is really, there is a need of new concept, right? And in fact, one of the needs that is highlighted there is the need to introduce new conceptual foundation for understanding the biological basis of the brain, and this going to development of theoretical data analysis tools, right? Anyway, let me see what I will discuss in this talk. I will, in fact, start by giving a quick overview of some of the imaging technologies used in biomedical sciences, especially neuroscience, because the imaging technologies have an impact in the type of theoretical tools that you want to use to deal with them, right, to address specific tasks. And I will give an overview of some of directional multiscale representation, because I'm going to use ideas from this area of applied mathematics to address some challenges in image processing. And then we'll show some applications, where I'm dealing with real problems, but I will emphasize aspects of the application where, in fact, the mathematics had some significant role there. Now, imaging, right? So there is a wide range, in fact, of imaging technologies available in biological areas. So, and they range in spatial resolution up to 1 nanometer, and this is the realm of electron microscopy, what people call EM. Now, this is, of course, the highest resolution technique, has the disadvantage that in order to apply, you need for the specimen to be fixed. Actually, you cannot use in vivo live images, right? So the next range of techniques is what's called under fluorescence microscopy. And here there are many types of techniques. Some of them, those that achieve high resolution fall under the area of super resolution, which is in fact a theme which has been very popular also outside people dealing with the engineering construction, like STOR, which is very popular. And there is also the confocal microscopy, which is something that I will consider more in detail. And some of the techniques, in fact, allow to take in vivo imaging, and I will discuss some of the properties that they have, right? Now, what is nice about fluorescent microscopy is the fact that, as I said, allows to image a specimen even in vivo, either being cultural or real tissue. And not only that, the idea of fluorescence, it allows to image and select subcellular compartments even at the molecular level with very high specificity. This is because over there people have discovered and created an array of fluorochromes. Those are chemicals with distinct and separable spectra that you can attach to molecules or even to molecules, right, in the specimen. So you can visualize simultaneously multi components in the specimen. So this is a quick table just showing that there is a bunch of these dyes, many of them under Alexa with a number, right, with separable spectra. And this, in fact, is an example of an image acquired with multispectral. So you acquire those simultaneously. You see this is, in fact, a single slice taken by a confocal image. This is a neuronal culture, and you see different molecular components of the neurons visualized associated with the different markers, right? Each channel, in fact, is associated with a fluorochrome which is selected to one specific molecular complex. For example, the red channel, FAN-NAD, is highlighted. I mean, this is the dye associated with the spatial Alexa, and that visualizes a very important component of the axon called the voltage gate encoding channel. This is involved in important mechanism. And sometimes people are interested, in fact, in studying specifically what is the spatial distribution of these molecular components within specific compartments. So, and these studies are done in over large set of images, and you see, so this type of problem they may give reason to. Now, confocal microscopy has one additional property. It is a device that has the ability to select in focus images at specific depth. So you have a system going from a pinhole, a collimator that allows you to, in fact, visualize a specimen and select one specific optical slice. So you can see multiple optical slices separately with resolution that go of this order, 0.2 micrometer horizontally and 0.5 vertically. So you acquire many slices, and when you put them together, if you can, you try to reproduce, this 3D structure of this object. And so those are the techniques that are available. Let me now talk about the kind of tools that I will bring into play, right, to address some problems of image processing here. Now, directional multiscale representation, right? Now, many of you are familiar with the fact that during the last decade, in the area of wavelet harmonic analysis, people have introduced a multiscale system going beyond conventional wavelets. Some of these ideas include, I don't mention all of them, in fact I select only two of them, the curvets that have been introducing for before 2002, but 2002 is the version that people usually refer to, and the other are Shearlets, developed in collaboration with Kangui Guo, Gita Coutinho, and Wang Qiu Lim, starting in 2005. And what the system do is, with respect to conventional wavelets, they are not only defined by taking a generator and applying a combination of scale and of dilation and translation. So they in fact form collection well-localized waveform that define over multiple locations scale of orientation. The orientation is one of the properties, together with the fact that they have support highly anisotropic. So in summary, what they do, they allow you to combine the classical multi-resolution analysis with the high directional sensitivity. Thanks to this property and the ability to, in fact, capture anisotropic information, these systems are optimally sparse in a precise sense for a large class of piecewise regular functions in R2 and R3. And another property that is closer to the application I have in mind is that when you apply them, when you use them with data, right, being 2D, 3D, they are able to capture singularities in the sense that they can capture their geometric information. Now, for what concerns the Shearlets, they are derived from the framework of a Affine system, which is the same mathematical setup where you construct conventional wavelets. And in fact, if you start from the affine group, right, the set of pairs made up of invertible matrices and element T in RD with appropriate group operation, you know that affine systems generated by psi and L2 of RD and the affine group are in fact the collection of functions generated by dilating and translating psi with respect to M in the group G, right, and T over RD. And if psi is chosen appropriately, if you can find an admissible psi, then this transform mapping F into this inner product between F and the element of the affine system is a linear isometry, so you can get reproducibility. You can produce the function at least in the L2 sense. Now, how do you get the Shearlet, right? So starting from the general affine framework, if you choose the dilation group in the easiest form, which is the diagonal matrix, the set of diagonal matrices, you obtain the conventional wavelets, because what you do in this case, you in fact dilate isotropically along each coordinate axis. While if you use a different approach, which is in fact consider dilation groups of this form, where you have two parameters, A and square root of A, this is what will give rise to the kind of the Shearlet system that I will describe in a moment. And what you notice here, in fact, that this matrix can be factored out as the product of this what is called the shear matrix and the anisotropy dilation matrix. So what happens is that this matrix is producing dilations, but they are different in the two coordinate directions, while the shear matrix is not dilating, right? It's producing something which is similar to rotations. Brief comment here, I use square root of A, but in principle you can use other type of powers, A to the alpha producing other type of anisotropy behavior. And the other point is that here, the use of shear rather than rotation has benefits, especially when you go to the discrete setting, because if you rotate, you may need to resample, right, when you go to the discrete setting, while shear is an operation that preserves the integer lattice. So this leads to some advantages with respect to possible curvets or other systems. Anyway, so what is the continuous Shearlet transform will be the special realization of the wavelet transform where I use the Shearlet group. And so for an appropriate admissible psi, I define my continuous Shearlet transform as this mapping from F in L2 over R2 in this case into those type of coefficients. They depend on three parameters, A, S, and T, right? So the continuous Shearlets, as a result, for an appropriate choice of the generator, will give you this collection of well-localized waveforms depending on the three parameter A, S, T associated with a range of scales, orientations, and locations. So these are not precisely orientation, but they're virtually rotation. They're in fact associated with slopes. I will not go into this type of detail. So if you want to see how they look like to get an idea, at least this is something that wavelet people usually like to see. If you look in the Fourier domain, the support of the Shearlets will be element of this type. So when A is 1, S and 0, you get these two trapezoid. When you dilate, you get those two associated with the expansion. And when you apply a different value of S, the elements are displaced. You see that they remain within the same vertical strip. So they are close to rotation, but not exactly. This is in fact the shear transformation. Now, one of the most interesting properties of the Shearlet transform is its behavior with respect to singularities, right? I mentioned before that these systems like curvelets have many other properties, for example, sparsity properties, but here I want to highlight one type of application and property that will be of interest for what we want to do. So the Shearlet transform is able, what I would say, to capture the geometry of singularities for multivariate function and distribution. Now, what it means can be made precise by a number of results. One is a group of results developed in collaboration with Erotinio and in another version by Philip Gross. They show, in fact, that the wavefront set of a distribution can be characterized through the properties of the Shearlet transform. Now, this result can be refined. Now, first of all, as compared with the continuous wavelet, there is a difference here. You know, continuous wavelets also have some nice microlocal properties. So you can in fact show that they do characterize what is called the singular support, which is in a certain sense the information about the location of the singularity. But when you talk about wavefront set, it gives you more, right? It gives you not just the location, but also the geometric information, like for example the tangent, right, to an edge. Now this characterization result can be in fact refined, and one can prove that for a general, actually, functions of 2 and 3 variable with piecewise smooth edges, one can characterize precisely the geometry of these boundary sets of these edges through the property of the asymptotic decay affine scales of the continuous Shearlet transform. And this includes not just smooth edges, which is what you would maybe assume by looking at the property of the wavefront, but also some sort of ability to characterize corner point junctions and Fourier singularities in R3. Here I mean Fourier singularity in R3, right? Corner point and junction, of course, are also true in the two-dimensional setting. And so there are several theoretical results of this type, and also some applied ones where these ideas are used, for example, for edge detection. Now here I just want to give you one specific statement just to make this list of results a little more concrete. I will present one theorem, just a statement of a theorem in two-dimensional setting here, just to show what you can do concretely in this case. So if, for example, B is the characteristic function of a set S is a compact set where the boundary is piecewise smooth, and also actually I need to assume I think simple, then I can in fact precisely describe the geometry of the boundary set through the asymptotic decay of the Shearlet transform as follows. So you remember that the Shearlet transform here is associated as three variables: the scale, the shear, and the location, right? Now if T, the location parameter, is away from S, or if T is on the boundary, yes, but S, the choice of this directional parameter, does not correspond to the normal orientation to the boundary, then I have this estimate that gives me that asymptotically the continuous Shearlet transform decays as fast as U. This is unlike what happens in this special set of points. So if T is on the boundary and S instead corresponds to the normal orientation, then the asymptotic decay will be precise of the order a to the 3 over 4. Now this number there, 3 over 4, has to do with the choice of the anisotropic dilation. So if you change the anisotropic dilation factor, you may get different type of decay rate. But the point is that you get slow decay at those locations, which is consistent with what you'd expect, in fact, from the statement on the wavefront set. And something more, in fact, you can also characterize the corner points in the sense that at the corner point you find two locations where the decay is low. So visually, this is what you would get. So if this, for example, is this compact set S with piecewise smooth boundary, and you look at the asymptotic decay rate, you see you get rapid asymptotic decay everywhere except at the boundary for non-orientation, and at corner points you get 2 points. And you can do something more sophisticated, but this at least gives the idea about how this technique can give you both theoretical and practical property that can in fact be usable. Now, let me now go over some applications here. I mean, are applications which involve the use of some of these techniques. They are not direct illustration of this type of results. So we'll in fact look at image analysis application focusing on two groups of problems. They come from problems in neuroscience imaging. Now I'm dealing here in problems of image analysis coming from fluorescence images of neuronal culture and brain tissue. Those are in fact two distinct types of data. And in one class of problems, I will look at the automated analysis of confocal images of neuronal cultures with the goal of computing, in fact, the spatial distribution of multiple analytes in selected subcellular compartments. And I will show this later. And now this is motivated, in fact, by problem of phenotypic screening. So people, in fact, use this test for in vitro models, for example, of brain function or comparing normal versus diseased brain. And so looking at the spatial distribution is relevant to this goal. And another type of problems I will also illustrate is the automated analysis, in this case, of two-photon image of brain tissue. This is also a technique from confocal or from fluorescent images, which is used especially when you're dealing with in vivo situation. And here the goal is specifically to, in fact, detect and analyze the morphology of dendritic spines, right? You remember that I said at the beginning there are, these two main functional units, the spines and the axon. In fact, this problem deals specifically with the axon. And this is motivated, again, by problem dealing with phenotypic identification. And here, in this case, analyzing the spines, in fact, is crucial for problems related to complex brain function, including psychomotor, affective, and cognitive domains. Now, for this type of task, I will describe a general platform, right, a pipeline of different modules. Typically, you start from data acquisition. Here I refer to confocal, but they can refer to a different kind of imaging technique. Here, for example, we may acquire multi-channel high-resolution 3D images, right, in stack. Then typically the first step has to do with data preprocessing. I will not say anything about this. This is rather standard. You can use, of course, multiscale techniques or many other ways here to remove noise and the blur. Segmentation is this important task, the first important task in the processing of the data when you want to, in fact, separate the neurons from the background, right? At this point, you have the segmented data, but the segmented data may contain many functional units, the soma, the dendrites, the axon, the spines. You want to separate them. Sometimes it's not possible to do them through spectral labeling, right? Especially, as you showed to you, one important problem is that it's not easy to separate the soma from the neurites. Neurites is the word describing globally dendrites and axons, because there is not a specific marker for the soma. Now, the other task here is the center line tracing. You want to sometimes find a trace, right, going through your structure to use as a local reference system for your images. And finally, once you have all this process done on the data, you may compute what we call globally associative measure. That could be, for example, characterize the morphology of the spines or compute fluorescence intensity in specific subcellular compartments. So let me address some topics taken from this pipeline. I concentrate on a few of the goals here. For example, segmentation, right? So the goal, as I said, is to separate the neuron from the background. And the problem is, especially when you deal with this type of data, there are difficulties due to the fact that the images at low contrast, they're topologically complex. They have large variation in object size and equal staining, right? The method that we use in this case is based on a somewhat standard application of support vector machine, but we use a method which is targeted, in fact, to deal with tubular structure. And these are some of the results we obtain. For example, this is the segmentation of confocal image of a neuronal culture. This is a segmentation we get on spines. The main tool here is, the main novelty is the fact that the feature that we use in the classifiers, and those that in fact give us the good performance, is the fact that we use filters which are geometrically very sensitive. In particular, we use both isotropic filters and filters derived on the Shearlet representation. Now, another problem that for which we found beneficial to use idea from a directional multiscale representation is what I call the soma detection. And as I said, and similarly to the other problem, again, the soma has not a predefined shape. They're not always round. They do not always have the same size. Also, you cannot separate them, as I said, using a specific marker or using intensity thresholding, because the intensity value is associated with the marker that you use to highlight special components, so that doesn't work. So we want to use something which is really based on the properties, and the idea that we use here is based on a multiscale geometric descriptor we call directional ratio, which is based on the Shearlet transform, and as you will see, has nice property to, in fact, separate vessel-like structure from blob-like ones. So this is the way it is defined. So for a function f in L2/2 at a scale a and t in R2, we define the directional ratio this way. So we look at the infimum over the supremum of the Shearlet transform, right, continuous Shearlet transform, by taking the infimum over S and the supremum over S. And this measure, I say, the strength of anisotropy. Intuitively, think what happens, right? As I said, the Shearlet transform is highly sensitive to the orientation. So if you are located on a vessel-like structure, there is an orientation for which this is very high or very small, so that the infimum will be much smaller than the supremum. Well, if you are in a location where the properties are somewhat isotropic, then the two numerator and denominator will be comparable, right? Now, this can be made precise, and in fact, we can prove a statement of this type, that if you look at what we call the cartoon neuron, so this is the cartoon neuron, is this characteristic function of a set made up of a long rectangle and a disk, right? And we have two scale parameters, little r and big R. And what we found is that we can prove that for a in a certain range, the directional ratio is very small when you are on the rectangle, while it is approximately 1 when you are inside the blob-like structure. So this is consistent with what I've said before, right? And so essentially this acts as a way to a geometric descriptor of the anisotropy, which is dependent on the scale. Anyway, we use this idea, therefore, to take a confocal image here. So starting from the data, we segment it. Then we apply the directional ratio. You see, red is 1, blue is, so red is 1, blue is 0. So you see that the red highlights the region inside. So we detect the somas. To fill them in, we need to do something else. We use, in fact, level sets there. And we can also separate the contiguous soma. Now, this same idea applies, in fact, also to images with multiple larger images, applies in 3D. And once we have, in fact, this property, we can combine some of the elements of the pipeline and describe. So if I take my data, I illustrate this on a single image, I can segment, detect the soma. Now, once we have detected the soma and the rest, we can, in fact, build traces. You see, those are traces going through the neurites. And we can go automatically and compute, measure of fluorescent intensity within those structures. Now, to wrap up, so similar ideas work also on images of brain tissue where, for example, we want to detect the spine. So this is an image, 2-photon fluorescent in vivo image of a brain tissue. So we can segment. And in fact, here what we can do, let me look this in more detail. We can, in fact, go and take a subvolume. I illustrate on subvolume what happens. I can segment. I can detect the spine, this through a property of the centerline trace, and extract the spine. And at this point, you can also compute and extract morphological properties there. So, conclusion. So, there is a compelling need in neuroscience to bring into the play some innovative computational analytical tools, and they are highly needed in the field. Directional multiscale representation provide one such tool with some useful properties that we illustrate in some examples. In fact, we show that they are useful in building this sort of pipeline for the automated image analysis in this type of data. And in fact, we are moving beyond this simple construction to deal with, in fact, problems of high content data screening for application, for example, in computational science and drug discovery. So I just acknowledge several collaborators. So this is my group at U of H. You definitely know, many of you will know Manos Papadakis. Ioannis Kakatia is also in computer science. Those are postdoc and students. This is a team at UTMB neuroscience. These are collaborators at Mount Sinai Hospital. And you can find references and code at my homepage. Thank you. No, those are not, in the image analysis tools, right, available are typically fall in two classes, commercial ones and the one that people make available on the web, right? Commercial ones, I don't know, Imaris, Metamorph, and so on. So we started developing these tools through, interaction with people working in the field. They found that essentially the commercial tools are typically too broad purpose or not sufficiently, don't work sufficiently well. So the tools that we have perform, I would say, significantly better than the one you found in commercial software. And they are available at the moment tested on real data, right? We work with people using this data for real application, but they are not available in commercially, but they're available for as some sort of freeware tools. Some of the tools described are available.